Hello, physical science students, and welcome to our new unit on forces and Newton's laws. This is going to be an exciting section. We're going to start by talking about forces. What are forces anyway? And how do unbalanced forces change motion? They do indeed. And how does that happen? Why does that happen? Also, we'll be looking at friction. That's a force too. What is that? What is going on with friction? So first let's look at just the idea of a force. What is a force? You can think of it as a push or a pull. Force can also include a change in direction. Force matters with, or direction matters with force. So, for example, this car turning, a force is being applied in order for that to happen. Here we see students standing on the floor. There is a force being exerted on their feet up from the floor. We also see the force of gravity in action right here, right? The force of gravity. You guys experience many, many forces. You exert many forces every day. You can think about all those forces that happen. When you kick a ball, you're exerting a force on that ball. Here, there's a force being exerted on this billiard ball. The net force, when we talk about net force, we are talking about the sum of all the forces acting on an object. So all the different forces that might be acting on an object, like this girl's foot, we have a force of the floor pushing up. We have the force of gravity pulling down. Any push, pull, stretch, turn, any of those different things, those are forces being exerted. So let's look at the difference between balanced forces and unbalanced forces. And what are we talking about when we're using these terms? When we have balanced forces, there is no change in motion. For example, the girl standing on the floor did not experience a change in her motion because the forces were balanced. And another example of the same idea would be your physics book lying on the table. When it is sitting on the table there is a force from the table pushing up on that physics book. There is a force of gravity that is pulling down on the book as well. But those two forces are balanced. So your physics book isn't moving up or down because the two forces are balanced. And notice again, direction matters with forces. So here's a question for you. If there is no motion, does that mean there are no forces? No. There are clearly forces acting on your physics book, but it's not moving, right? It's just that the forces are balanced. The only time we have no motion is when forces are balanced. They are all in balance. If an object is in motion, does it always have a force acting on it? Now there's an interesting question, right? So it's important to remember that a force is only needed to change an object's motion. If you could imagine some object being hurled through space with no, it's far enough away that, gravitational effects are negligible. There isn't an atmosphere to cause air friction. There is no force acting on that object, and that object will experience no change in its motion unless a force does act on it. If that object comes into contact with a planet and it gets kind of close to that planet, it's going to start experiencing gravitational pull from that planet. So and its motion will change. So a force is needed only to change an object's motion. Unbalanced forces change motion. If you have forces acting on an object and they are in perfect balance, there will be no change in motion. There are two forces at work here. If you have unbalanced forces, we have a force here going this direction and it's unbalanced. It is not balanced by an opposing force. There will be motion in that direction. Pretty intuitive and pretty obvious, right? And remember, the net force is simply the sum of all the forces acting on an object. Here, if we look at the net force would be this direction, right? Because we have the sum of all the forces acting on that object are giving us a net force that is in that direction. So how can we find the net force that is acting on an object of all these? We have a few different rules for adding forces. Here we add, number one, add forces that are in the same direction. So here we have an example of forces in the same direction. This little guy is pulling, this guy is pushing. We have a push and a pull that are going in the same direction. We have a net force of 2. If these are equivalent amounts of force being applied, we have 2 to the right. If we have forces in opposite directions, here these guys are pulling and these guys are pulling this direction, and they're opposite directions, we're going to subtract or add negative value, either one, because it's the same thing. We have 2 to the left and 4 to the right. If we would consider going to the left positive and this negative, we're ending up with a total of a -1. It's 3 minus 4, -1. Or you could add the negative, add a -4. So you do that either way, and we end up with 1 to the right or a -1, or however you want to look at that, however you're defining your coordinate system. 3, forces that are not in the same direction or not in opposite directions cannot be directly added together. And lucky you, we're not going to learn how to do that. That's a little bit more difficult math, and we're not going to look at how, but you can't directly add or subtract those. Now let's take a look at friction. You've all heard of friction. What is friction anyway? Friction is a force, and it is a force that opposes the sliding motion of two surfaces that are touching each other. If we have something, a block sitting on the table, and you exert a force to push that block, there is another force called friction opposing it. In the opposite direction, it is opposing that motion. So this is just showing, remember our physics book lying on the table. We have, remember, the table pushing up, gravity exerting a force down. We have friction exerting a leftward force if we are exerting at the same time a force to the right. So those are all the different forces that are going on with that physics book when we try to push it across the table. So what causes friction? It's a good question. If you ever look at a piece of stainless steel, pots and pans are often made out of stainless steel. They appear very smooth, but if we take a very close look at them with high-powered microscopes, scanning electron microscopes, give us a very close look at what a piece of the surface of a piece of stainless steel would look like. It actually has a lot of bumps and ridges, and it isn't perfectly smooth. If we were to take a piece of that, and here's kind of the idea of a cross section of a piece of something that we maybe think is smooth and something else on top of it, and put those surfaces together, friction is caused when there is sticking because those little bumps touch each other. If we put more force down and between the two surfaces, we will also increase the force of friction between them. In order for friction to be overcome, a force needs to be exerted to overcome that friction. Also, the amount of friction is definitely proportional to the amount of surface area and bumps that are actually touching each other between the two surfaces. So, obviously the material will matter, and you guys all know that. different materials will slide over each other some easier than others. So the material will definitely matter on how much friction there is between the surfaces of the two. Also, how much force is actually being applied between the two. If you have a very heavy object sitting on the surface of a floor, there will be a lot of friction because there will be much more force that's exerted pushing those two surfaces together. There will be many more of those bumps in contact with each other, and you'll have a lot more friction. So let's look at a few different types of friction. 1, static friction. Static friction prevents two surfaces from sliding past each other. Here's an example. We have a little family they're sitting on their sleds and they'd like to go sliding down the hill, but the force of static friction is preventing them from moving. In this case, the net force is 0. They are not moving down the hill. They are staying still because the static friction is canceling out any force that would be pushing them down the hill. We have another kind of friction called sliding friction. This opposes the motion of two surfaces sliding past each other. So as this group of individuals is sliding down the hill, let's see if I can get they're sliding down the hill. There is another force, the sliding friction, that is going this direction. The sliding friction. The sliding friction is less than the movement of that sled. The force of the sliding friction is less because obviously the sled is moving. So we have a really big force going this way and kind of a small sliding friction force this way. Generally, sliding friction is less in magnitude than static friction. Let's look at rolling friction. You might think of friction as a disadvantage or something that's not good in your car, but actually your tires wouldn't even work if we didn't have rolling friction. If you think about the tire here, or a wheel of any kind, rolling friction is the friction that occurs when it is in contact with the surface area, the ground. And it actually is what allows the wheel to roll. Without rolling friction, wheels wouldn't really work. You can think of rolling friction as a very special type of static friction. Right here at this point is where we have the static friction. And it's necessary in order for that wheel to roll. That is what allows it to push off of the ground and basically roll around. You've also seen or experienced perhaps getting stuck in the snow or on ice and push the gas on the car and the wheels just spin and you go nowhere. That is a case where rolling friction would be really nice to have. In that case, where the wheels are just spinning around, the force used to rotate that tire by your car is greater than the force of any of the static friction around. And it would be really nice if that static friction was greater for you at that moment, because then you would be able to get unstuck. A lot of times people use the term traction. How good is the traction on your tire? Or you need some traction. And what they're really referring to is friction. So another question to ask, does surface area affect friction? Well, it may come as a surprise, but friction is nearly independent of the macroscopic surface area in contact. And the reason is this. You know that friction depends on those little microscopic bumps that are in contact when the surfaces are pushed together, right? So if the macroscopic contact area increases, and just as long as the mass of that object stays the same, more of those little bumps are formed that are going to touch. However, because pressure equals force divided by area, the total pressure pushing the surfaces together would decrease. And that causes the contact area on each of those bumps to become smaller so that the total microscopic contact area remains nearly unchanged. And so just remember that when you increase the surface area between the two, the total friction really is not going to change because you basically distribute that pressure more evenly across your larger surface area because you have more of those little bumps that are sort of taking away from the pressure on any one of those bumps, sort of evenly distributing that across. Advanced idea. Set up your own experiment. Read through this. See if you can figure that out. Other ideas too. Some of these frames had the word normal friction. What is normal friction? Look into that and look forward to seeing what you come up with. See you in class.